So now we're going to look at exponential functions. And so we're hitting SOL number 2 again. We've already talked about in this course polynomial, rational, and radical. Now we're up to exponential functions. These are the module learning outcomes. We will apply the concepts related to exponential functions, evaluate exponential functions, graph and analyze exponential functions, solve exponential equations, solve compound interest problems, and solve applications involving compound continuous problems. So exponential functions are extremely important in both economics and science. Exponential growth functions allow us to discuss the growth of money in a money market account as well as the growth of population. Exponential decay functions can be used to model radioactive decay or define how old an object is. In an exponential function, the growth or decay rate of the function depends on the current value. So how fast it's growing or how fast it's decaying depends on the current value. So we'll let b be any positive real number such that b does not equal 0 and c be any non-zero real number. Then for any real number x, f of x equals c b to the x defines the exponential function with base b. The base b is called the growth factor and c is the initial value. And you want to note that the domain is all real numbers. So notice it's very different. Up to now, when we've been working with our functions, we might have something like f of x equals 3x squared minus 7x plus 2, where x here was the variable in the base. My exponent was a number. This is now flipping on the head. So now what we're looking for exponential functions is something that looks like this. Like 7 times 3 raised to the x power. We're flipping around the base and the exponent here. When the base or power of an exponential is not a nice, easy number to work with, it's important now how to evaluate using a calculator. For instance, if we want to evaluate 4.65 raised to 2/3 on a calculator, we would enter the base, hit our exponential key, enter in 2/3, and hit equals. The sequence of keys might look something like this, kind of depending on your calculator. For those that are using your TI 30XS, your magical key is going to be the caret key right here. It's catty corner from the 7. So if I need to enter in that 3 to negative 5 over 4, I type my 3. I'm going to hit my caret key. So again, I'm hitting this key right here. That should shift up there, things up there. I'm going to do my negative sign next to the enter key. I'm going to do my fraction key, 5 over 4. And kind of right arrow a couple times to get back down, and then hit enter. And here they asked us to round off to 4 decimal places, so that rounds off to 0.2533. Let's see if we can do this next one. So I'm going to do parentheses. Second square key gives me the square root. I'm going to type 15. Make sure you hit your right arrow key to get out of there. Then close the parentheses, caret key, and then I'm going to hit my pi key. Hit enter. Again, rounding off to 2 decimal places, this is what you get. Or 4 decimal places, excuse me. And let's try this last one. I'm going to enter it exactly how I see it. I'm going to do 4 times, parentheses, fraction key, 3 over 7. Hit my right arrow key, close it. Do my power, negative 1.5. Now, make sure you hit your right arrow key. You got to get back down before I put in that subtract 3. And then we round it off to 4 decimal places. So make sure you can do this on your calculator. Reach out to me if you or with a tutor in Math World if you need help doing it on your calculator. So here we want to make a table of values and graph the following. So I have my functions 2 to the x, and if I take 2 caret 3 raised to negative 3 power, notice I get 1/8. That's because in mathematics, r to the negative n power is the same thing as 1 over r to the n. So 2 to the negative 2 would give me 1 over 4 squared, which is 1/4, so on and so forth. And so you can go through, you can generate this table of values here by plugging these different values of x. Let's see what happens if we use the table feature here. See if we can do that on our calculator. So let me clear that out. So I'm going to put my 2 caret key, variable key. I'm going to start this at negative 3. I'm going to clear that step by 1. See what it does. So here's my table. 1 over 8, 1 over 4, 1/2, 1, 2, 4, and 8. And I can keep going, but I think this is sufficient. Same thing's going to happen with 3 to the x. So if I were to do that here, I would just change that base to a 3 and enter. And I want to start at negative 3. There's my table of values. And I can even do it with my base. I could do this with any base here, so I could do it with 4. That generates our table here. Now, if you're to graph these points, you get this shape here. For 2 to the x compared to the 3x, it looks the same except it's a little steeper. And for 4 to the x, it's still pretty much the same, but just kind of more extreme, more steeper. So notice that these functions have the same base, except though the base gets bigger. The graph gets steeper. In general, if b is greater than 0, b to the x will have this shape. And notice here that this does have a horizontal asymptote, y equals 0, even though it's only in one direction, going in this direction. Now, let's look at when our base is between 0 and 1. Well, 2 to negative x, well, 2 to negative 1 is 1/2, 3 to negative 1 is 1/3, 4 to negative 1 4. Now, just think for a moment before we do this. If I have a negative in front of my x, and we briefly talked about this back in chapter 6, this is going to give me a horizontal reflection. So 2 to negative x, which is the same thing as 1/2 the x, this should be 2 to the x reflected across the y-axis. So all my pictures I have here should be flipped over like that for each one of these. Sure enough, if you do the table of values and plot the graph, that's exactly what you get. So notice here that these functions, when my base is between 0 and 1, they have the same basic shape. So let's summarize. So the graphs and examples C, D, and E are the graphs. Example A, B, and C reflect across the y-axis. And so we just summarize here. When my base is greater than 0, this is what my graph's going to look like. And it's always going to have these 3 anchor points, negative 1, comma 1 over b, 0, 1, and 1, comma b. So if my base is 4, my anchor points will be negative 1, comma 1/4, 0, 1, and 1, comma 4. If my base is between 0 and 1, then this is going to be my graph. And so notice here that, like, let's say b was 1/3. If I take the reciprocal of 1/3, that'd be 3. and this would be 1 over 3. Again, the same anchor points. For both of these, the domain here is all real numbers. The range are the positive real numbers. They have a y-intercept of 0, 1. There are no x-intercepts. It gets really close to the x-axis, but never hits the x-axis. There are no x-intercepts. This one actually rises or increasing, so we say this is an exponential growth function. This is decreasing. This is called what's an exponential decay function. Both of these functions are 1 to 1, so we're going to see that they have an inverse function. We'll see that in the next section. Let's see, and the graph always contains these points, and we already mentioned they have a horizontal asymptote. So let's go ahead and take a look at some workbook problems. So here, we're going to go and manually do this. I know we did it on the calculator, but we're going to manually do this just so we can kind of practice how it works. So I'm going to take my -3, -2, -1, 0, 1, 2, and 3. 3 to the -3, again I flip it, it's 1 over 3 to the third. That's 1 over 27. 3 to the -2 is 1 over 3 squared. That's 1/9. 3 to the -1 is 1 over 3, which is just 1/3. See if I can draw that a little bit better. 3 to the 0 is 1. 3 to the first is 3. 3 squared is 9. 3 to the third is 27. So if I start plotting these, -3, -1, that's really, really small. So that's like almost right on that axis, that x-axis. -2, 1/9 is not much better. -1, -1/3. See if I can draw this. Oh boy, that didn't work very well. Must have had something on there. Sorry about that. So 0, -1 is about here. 1, 3 is here. 2, 9 is here. 3, 27 is up here. So let's see if we can connect our dots. My domain here is going to be all real numbers. My range, this is going to start just above 0. Be 0 to infinity. Horizontal asymptote is y equals 0. Yeah, I don't know why that didn't erase. Must have gotten something on the eraser on the pink pen. It's got the same exercise. So again, I'm going to do -3, -2, -1, 0, 1, 2, and 3. If I raise a half to the -3, I flip it. That gives me 2 to the third, which is 8. That gives me 2 squared, which is 4. That gives me 2 to the first, which is 2. That's always going to be 1. That'll be 1/2. Half squared is 1/4. Half cube is 1/8. So make sure I don't erase with the pink. Okay, so -3 is 8. So that's up here. -2 is 4. -1 is 2. 0, 1. 1/2. 2 1/4. 3 is 1/8. Again, I'm not going to erase here. So I'm going to draw my graph this way. So it's going to look something like that. The domain and range don't change here because there's no shifting. So this is still going to be negative infinity to infinity, 0 to infinity. Horizontal asymptote doesn't change either. It's still y equals 0.